Hi, this is the fourth lab, which is going to be about oscillations. So in order to do this lab, we're going to need to talk about several essential formulas, which include the spring force formula, which is negative spring constant times length times relaxed length, gravitational force, which is equal to mass times gravity, kinetic energy, which is equal to 1/2 mv squared, gravitational potential energy, which is mass times gravity times height, spring potential energy, which is 1/2 k, which is spring constant, times length minus relaxed length, that quantity squared, and finally the energy principle, which is equal to delta E is equal to W plus Q. Furthermore, I also need to talk about my predictions, and my prediction would be that the energy principle will be conserved because of the fact there is no thermal energy and work present, and therefore would be equal to 0. Now we're going to look at the Python code. In order to do this, we're going to first need to note some of the system properties, which include the mass of the ball attached to the string, which was 0.402 kilograms, the initial position of the ball, which was negative 0.113, comma, negative 0.621, comma, 0, and the initial velocity was also 0, and time started at 0. Furthermore, from the video analysis, we also know that the spring constant is equal to 6.83, and that the relaxed length is also at 0.123 meters. Now, these three lines of code help calculate the kinetic energy, gravitational potential energy, and gravitational spring energy, which I noted before. Now we're going to look at the next part, which is calculation of the net force, which is summation of the spring force and the gravitational force, in which that the gravitational force is always pointing down and the spring force is always pointing in some direction up, mainly at the origin. And once we calculate the net force, we're going to use that to help calculate the velocity of the ball, and then ultimately use the ball velocity to calculate the position of the ball. And once we know that, we're going to use that to calculate the kinetic energy, gravitational potential energy, and spring potential energy, and ultimately calculate the change in each of those respective energies after each iteration and graph that on a graph seen over here. And the graph, when run, looks like this. Ultimately, you can note several different oscillations: yellow, blue, red, and green. Blue being kinetic energy, red being the spring potential energy, green being the gravitational potential energy, and yellow being the total summation of all the energies. And note that yellow is equal to 0 the entire time, so because of that, you know that energy is conserved and that the system is also contained. Furthermore, if you look at the graphical representation on the left, you see the blue ball, which is the expected orbit, is closely followed by the red ball, which is my observed orbit, and which is derived from the position values of tracker. And if you watch the entire time, you note that it follows it very closely. So because of that, it seems like a very good representation of oscillation and gravitational potential energy and total summation of the energies nonetheless. And we can confirm that with the other file that can help us calculate all the energies, and can basically compare the two energies via this. As you can see, the two graphs, which represent the tracker data and the expected path of the spring, are close to each other, but yet there's still differences nonetheless, which might be derived from dissipating energy forces, such as thermal energy, and that some of the energies are actually going to heat up the spring, and another force might include drag force, which might slow down the object, which explains why the amplitude of each oscillation of the tracker graph isn't as high as the expected graph. Now we're going to go into the lab questions. The first one states that for your model system, is the energy principle satisfied? And I said yes, because the energy principle stated that delta E is equal to work plus Q, and W is equal to 0 because it was a closed system, and Q was 0 because it had no thermal energy. Therefore, delta E was equal to 0. And as you can see, the only energies that were acting on this system were the gravitational potential energy, spring potential energy, and kinetic energy, and which you all see, they all resulted in the yellow line, which made the thing equal to 0, and therefore it was satisfied. Furthermore, this also answers my hypothesis in the beginning, because in the beginning I made a observation that there was no work or thermal energy acting on the system, and which led the summation of all energy forces equal to 0. And because of that, the energy principle was satisfied. For the second what does it mean question, it asks us to compare the two oscillation periods between the x coordinates and the y coordinates. And basically, in order to do that, we're going to need to find the period of oscillation, which is, in this case, is equal to total time over the number of oscillations as derived in each of the graphs. And the first one happened to be about 1.65, and the second one happened to be about 1.51. And these are different because we calculate both of them to be oscillations of spring, when in reality the x-coordinates are an oscillation of pendulum motion and the y are oscillations of spring motion. Hence they're different.